In this video, we're going to talk about experiment 15, which focuses on the titrations of acids and bases. So titrations is a concept that you worked on in class with your instructor, and you guys looked at this in the context of the titrations of acids and bases. And most notably, you looked at this in the context of strong acid, strong base, and you also looked at the example of a strong acid or base and a weak acid or base. So that was how we kind of focused on titrations in class. So we're going to use our understanding of titrations. We're going to kind of remind ourselves about some of the key aspects of what a titration is in the beginning of this presentation. And then we're going to look at how you actually set that up experimentally and accomplish a titration in the lab. So the first question is what is a titration? Well, the goal of a titration is to determine the concentration of an unknown. Now, we have to start using some of the vocabulary words that go along with titrations. So typically, the unknown, or the solution where we don't know the concentration and we're trying to figure out that concentration, that's called the analyte, the thing that we're trying to analyze. And we do that by using what we call a titrant, and the titrant most often is a solution where we know the concentration very accurately. Typically, that's done through a process of standardization, meaning we've done some process to determine very accurately the concentration of the titrant. So generally speaking, the titrant, we know the concentration of the titrant. The analyte is the thing we don't know, and then by combining them together, we can figure out what the concentration of the unknown is. So let's talk about what types of reactions can be studied by titration. Now, from class, we've harped on the acid-base titrations, which are very common. But you can also do other types of reactions by titration, and one of the more notable ones is redox reactions. So in redox titrations, you can use an oxidizing agent or reducing agent as your titrant, and then in the analyte, you would have the other, meaning if, for example, you had an oxidizing agent as your titrant, in solution, you could have a reducing agent in your analyte, and then reacting the two together will give you a redox reaction. Another one that's very common is precipitation reactions. So you can precipitate an ion out of solution by titration to discover what the original concentration was. That's sort of similar to gravimetric analysis, but what distinguishes titrations from other methods like gravimetric analysis is that we don't weigh the product in particular. In general, we use some kind of indicator to determine what we call the equivalence point or the end point. And I'm going to talk a little bit about what the difference between equivalent point and end point is. But in this case, we use an indicator that will tell us when we've reached the point where the moles of the titrant is equal to the moles of the analyte by stoichiometry. And then from that relationship, we can determine the concentration of the unknown. Knowing that the moles are equal and knowing how many moles of titrant we added, we can then work to figure out the concentration of the analyte. So let's look at how we set up a titration. Now, I'm going to kind of go through some of the basics first, and then we're going to look at a video that walks you through all of the steps of a titration in detail. So I'm going to kind of give you some introduction, and then we'll sort of break it down where you can actually see the whole thing being set up and being performed. So the first thing that we have to look at is the apparatus that we need. So one of the main pieces of equipment we need is a burette. And a burette is a graduated tube used to dispense measured quantities of the titrant. And again, the titrant is a solution of one of the reactants with a known concentration. So we know the concentration of the titrant. The concentration of this solution is generally determined by a process known as standardization. So we're actually I'm going to explain to you how we do a standardization, and that's a key component of this experiment. We have to standardize our sodium hydroxide titrant that we'll use to figure out an unknown. Now, burettes are a very interesting piece of equipment. When you look at a burette, so this is kind of the top of the burette. This is the bottom of the burette, and this is the stopcock. And the stopcock is what allows you to kind of control the amount of volume that's dispensed. And you can turn this knob, and it'll either go faster or slower in terms of how much liquid comes out. Now, what's interesting about a burette is how it's graduated. So you'll notice that this burette is graduated, and it's in milliliter. The largest increments are in milliliters. So you see 1, 2, 3, 4. And then between the milliliters, there are additional graduations that divide the milliliter into 0.1 ml increments. So in theory, we can directly read off of this 1.1, 1.2, 1.3 mils, for example. And then remembering how we use these graduations, not only can we read to the 0.1 mils, but we can actually go a little bit further, and we can estimate between the 0.1 mils to get an estimate of the hundredth of a mil place. So when you're reading a burette, you're always going to want to write your volumes as having 2 decimal places. So the one that you're going to read off is going to be one of the graduations, and then you're going to sort of use your eye to estimate between the 2 graduations to get the second decimal place. So now how do we measure the volume dispensed by a burette? Well, in general, what we do is we fill the burette up to some given point, and we measure that volume. So we call this the initial volume. So you're going to read that off. So let's say, for example, we filled it up to 3.35, which would be somewhere in here. That's where we're going to start from. And then we're going to add however much volume we need in order to do our reaction. And then we are going to get to what we call the final volume. So this is when the reaction is complete, we're going to have our final volume. And again, we read that to the second decimal place. So the volume dispensed is going to equal the final volume minus the initial volume, meaning where did we start and where did we end? So that's how we get the volume displaced. So that's how you use a burette. And then the other thing that's really important is the analyte. And typically the analyte is contained in some kind of flask or beaker. A very common flask to use is an Erlenmeyer flask. It just kind of helps to prevent splashing. But actually in some experiments we use a beaker to allow us to put in a pH probe. So it kind of depends on what type of experiment you're doing. But the analyte is the solution containing the unknown concentration of the other reactant. So this is the unknown component typically that's in the Erlenmeyer flask. And then the indicator is a compound that is added to the analyte, which gives a visual cue when the endpoint is reached. So when you're doing a titration, we need to figure out when the moles of the titrant equals the moles of the analyte. And to do that, we can't just, if no color change is happening, we can't just look at it and sort of see the solution with the moles. We need something that changes in order for us to know that we've gotten to the point where the reaction is complete. And that's what the indicator is for. So when the indicator changes color, that is when the endpoint is typically reached. Okay, so now let's take a look at this video, which is going to go through and show us all the steps of setting up and performing a titration. So this video is actually from Carolina, and they do a really good job of explaining how to do a titration. So we actually use Carolina burettes at Fordham. So this video will show you exactly how to do a titration.
Including a burette, ring stand, and a burette clamp. A burette is a long, narrow, graduated tube used to add titrant. It has a stopcock to regulate the flow of liquid. Notice that the markings on the burette go from lowest at the top to highest at the bottom. The ring stand and burette clamp are used to mount and secure your burette. Other materials you will also need include a small funnel to help you fill the burette, a 125 milliliter Erlenmeyer flask, which works best for titrations. The shape of the flask allows for more vigorous swirling than a beaker or other glassware and minimizes spill hazards. A volumetric pipette and pipette bulb to transfer a known volume of analyte to the flask. A wash bottle filled with deionized water, a beaker or flask of titrant and of analyte, indicator selected for your reaction, a reading card to help read the meniscus, and a sheet of white paper to help visualize the endpoint. To prepare your burette for the titration, it is good laboratory practice to rinse your burette thoroughly with deionized water, then with a small amount of titrant. After each rinse, open the stopcock to allow the liquid to drain out the bottom. If there is a lot of liquid clinging to the walls of the burette, then thoroughly clean your burette and repeat the rinse process. The accuracy of this technique is dependent on the titrant flowing into the flask and not sticking to the walls of the burette. Mount the burette in the clamp, making sure it is positioned vertically, and there is enough room to position your flask underneath the tip. Check to see that the stopcock is in the closed position. Insert the funnel into the top of the burette and fill with titrant almost to the top. Filling exactly to the 0 mark is not necessary, but you do need sufficient titrant to complete the reaction. Check the column for air bubbles and gently tap to free them from the side walls. Remove the funnel. Place the Erlenmeyer flask under the tip and open the stopcock to allow a few milliliters of titrant to flow through, releasing any trapped air. Rinse the tip of the burette with water. Empty the liquid into a waste container and thoroughly rinse the flask. It is not necessary to dry the flask. Record your starting volume. It is important to accurately read the volume on the burette. First, note that the liquid forms a concave meniscus because the water pulls itself up the side walls of the glass. You should read the volume from the bottom of the meniscus at eye level. Secondly, it is important to read your volume to the correct number of significant figures. This burette indicates volume to the nearest 0.1 milliliters. With any graduated glassware, record the volume to one additional decimal place beyond the smallest graduation. In this case, record the volume to the nearest hundredth of a milliliter, estimating the final place. Use the volumetric pipette to transfer the analyte to the flask. Add a few drops of indicator to the flask and swirl. Place the flask under the tip of the burette. Record this volume. Placing a piece of white paper under the Erlenmeyer flask may make it easier to detect the color change. Operating the burette requires 2 hands. One hand turns the stopcock, while the other hand swirls the flask. Practice turning the stopcock a few times to familiarize yourself with how quickly the flow starts and stops. It is common laboratory practice that the first titration is an estimate. Open up the stopcock and allow the titrant to enter the flask quickly. Continuously swirl the flask. As the volume of titrant in the flask increases, the color of the indicator appears, then disappears as you swirl. When the analyte becomes a colored solution, close the stopcock. Record the final volume of the burette. Subtract the initial volume from this final volume to get the estimated volume of titrant needed for this titration. Knowing the volume that is a little past the endpoint, subtract 5 milliliters from that number to get the amount of titrant that can be safely added before a slower addition is required. As the estimate titration shows, a dark-colored solution indicates an excess of titrant has been added. The desired endpoint is a pale, faintly colored analyte. To reduce the risk of passing the endpoint, slow down the addition of titrant when flashes of color begin to appear in the analyte. Adjust the stopcock to slow the flow of titrant to a dropwise rate. Continue to swirl the flask with one hand and keep the other hand ready to close the stopcock. When you notice the indicator taking longer to fade, close the stopcock. Rinse the tip of the burette with deionized water and swirl the flask. Record the final volume on the burette. If the analyte remains faintly colored, then you have reached the endpoint. If the analyte is still colorless, then repeat these steps. Add a drop, rinse, swirl, and record until a faint color persists. Typically, titrations are performed in triplicate. Use the average volume of the titrant required to reach the endpoint for any calculations. You now know how to properly perform a titration. Be sure to check out the second video in this.
Okay, so let me just make a couple of comments because so that basically takes you through the whole process. But there's one thing that you might be a little confused about, and that's this whole very quick first reading. So what they're doing is let me just find that where that is.
Volume. Placing a piece of white paper under the.
So what they're doing is in the very first titration that you do. So in our lab, we're going to do 4 titrations. The first titration is going to be one where you kind of do it quick. So, and the goal is just to get an approximate value for the amount of titrant that you need, right? Because if you go you'd have to go so slow on the first one to figure it out that it would be a waste of time. And you can do this much more efficiently. So what they do is they take one and they say, this first one, I'm just going to do it quick, just to get an idea of how much of the liquid I need to add from the burette. And that's what they do. So in this case, he adds the titrant.
Familiarize yourself
really quick.
with how quick.
So he's kind of just putting it in real fast. And you can see that when he's done, we'll take a look when he finishes here. When he's done, he gets this really bright pink solution. So you get this really bright pink solution. And what he said, and he kind of said this quickly, was that because it's so bright in being pink, that there must be an excess of the titrant. And that is true. The more sodium hydroxide you add, the more pink the solution will get after you get past the equivalence point. We're going to talk about this in more detail in a few slides. So what he's done here is he's not using the data for this titration to determine the unknown concentration. They just figured out that you have to add about 10 mils. They do that. They calculate how much he added. You have to add about 10 mils, and then the thing is going to change colors somewhere before 10 mils, maybe about a half a mil before 10 mils. This thing is going to change color. So then what they do is now they know, well, okay, 10 mils is too much. So I'm going to do my next titration. I'm going to go to about 5 or 6 mils, which I know should be totally safe because it's going to change it around 9.5. And then when I get to 5 or 6, I can just open the stopcock up, go right to 5 or 6 mils added, and then I can start to slow it down and add smaller portions until I get it to being very close. And the way you know it's very close is when you add some and it takes a long time to go away. So let's take a look at what he's kind of talking about at that point. Okay, so I zipped ahead a little bit. So you can see, so he starts adding. And then now, as he adds it dropwise, you see how long it takes for that pink to go away? That's an indication that we're getting very close to the endpoint. And then what he's looking for, and he shows it here, what you want when you get there is you want to have a solution. So these are the solutions. This solution has gone well past the endpoint, way too pink. This solution is almost perfect. There's a teeny bit of pink that you can see looking through that solution. It's almost clear or colorless, but there's a teeny little bit of pink. That means you've hit it right on the nose, right? You want just the teeniest bit of color, and then you know you've gotten to the point where you just have the end point, where it's gotten to the point where the sodium hydroxide is now starting to be just in a teeny little bit of excess to give us some color. So that's a distinction I wanted to make, and just something that I wanted you guys to be aware of. So this one is what we would consider to be accurate. And then you're going to do 3 of these where you get a nice accurate result, where you get a very accurate volume and the color is barely pink. Okay, so now let's look at what we call the titration curve and the equivalence point. So now a titration curve, and we're going to look at a titration curve in more detail in experiment 16. A titration curve is a little bit different. It's a little bit different from using an indicator. So when we use an indicator, we get the equivalence point by seeing the color change. But a bit more accurate way of doing it is to collect what we call a titration curve. And when we collect a titration curve, we do the exact same thing as what we did before, but we stick a pH probe into that solution. And what the pH probe does is, as we add volume, we can actually measure directly what the pH is. So in this case, we can actually see what's happening to the solution at all points along the adding volume from the burette. So rather than using an indicator to change color, we actually use a pH meter to measure the whole change in pH over the course of the volume. So you'll notice that what we have on the y-axis is pH, which is coming from our pH meter. And on the x-axis, we have the volume of the titrant that's added. So in this particular reaction, and what this titration curve is generated from, is where we have a known concentration of NaOH, which is 1 molar in our burette, and a known concentration of HCl. Now normally this would be an unknown, but we're using a known here because now we can actually start to figure out what's happening in our titration curve. So in this case, it's 50 milliliters of a 1 molar HCl solution. And so just so that we're all on the same page, I throw up the reaction right here so we can see that HCl plus NaOH gives H2O plus NaCl. So now let's start to look at what this titration curve shows us. And then what we can do is we can start to see where, then from this, we can start to look at what is the difference between a titration curve and how does using an indicator impact our results? Okay, so the equivalence point is defined as the point in volume, meaning at some point along here in the volume added, we're going to get the number of moles of the titrant to be stoichiometrically equivalent to the number of moles of analyte. Now, the reason why I say stoichiometrically equivalent is because oftentimes people will just say that the moles of the titrant equals the moles of the analyte. But that is true only if there's a 1-to-1 ratio in the reaction. So here, there is a 1-to-1 ratio. So it will be true by stoichiometry that the moles of the titrant will be equivalent to the moles of the analyte. But things get a little bit more complicated if you have more than one, if your stoichiometric coefficients are not 1-to-1 or 2-to-2. Meaning if we had a reaction where it was a 1-to-2 ratio, then the equivalence point gets to be a little bit more complicated. And we're going to actually look at that in experiment 17, where we have a ratio that's not 1-to-1, but is 1-to-3. And we're going to see what the impact of that is on the so-called equivalence point. So now let's start to do some calculations. So if we know what the equivalence point is, being that the number of moles of the titrant is equivalent to the number of moles of analyte, we can start to do some math. So in this case, we know we can figure out using the volume and the concentration of HCl how many moles of HCl we have. So then we can ask ourselves, what volume of NaOH would be required to reach the equivalence point? So let's start to do some math. So let's figure out the number of moles of HCl that we have to work with and react. So we have 0.0500 liters. I basically took this 50 mils and converted it to liters, dividing it by 1,000. And we know that our concentration is 1.00 moles per liter. So when you multiply 0.05 times 1, you get 0.0500 moles of HCl. And then we know that at the equivalence point, the moles of the HCl are going to equal the moles of the NaOH. That is the definition of the equivalence point, when the titrant and the analyte are stoichiometrically equivalent. So at this point, then, we know that if we have 0.0500 moles of HCl, then at the equivalence point, we must have 0.0500 moles of NaOH. So now the question is if this is how many moles of NaOH we have to deliver into that analyte to get to the equivalence point, what volume of NaOH would we need? So what we need to do is we need to use the molar concentration. For every 1 mole, there is 1 liter based on the 1 molar concentration of the NaOH. So this gives us 0.0500 liters or 50 milliliters. So we know that at 50 milliliters precisely, that is when we have our equivalence point. So we can put a little line there. So when we hit 50 mils based on our calculations, we know that at this particular point, and it's actually this exact point right here. I know because I created this graph. So this point is the equivalence point. So now let's take a look at what this graph shows us and start to analyze what's kind of happening here. So when we first start this reaction, let's look at sort of the graph. This makes sense. When we first start at 0 volume of titrant added, we just have some 1 molar HCl around. And if you use the calculation to determine the pH of this, if you take negative log of 1, you're going to get a pH of 0. And that's why this thing starts out with a pH of 0 at volume 0. We can actually calculate that directly because our solution is starting at 1 molar HCl. So the reason why at 0 we have a pH of 0, that's just because of the concentration of the HCl. Now, let's look at this in terms of adding some NaOH. When we add base to a solution, it doesn't matter what the base is. If you start to add base to a solution, the pH is going to go up, right? We're going to start to go toward more basic pHs. So that's what starts to happen. As we add base incrementally, the more and more base we add, we're going to raise the pH. And that's what starts to happen. As we add 5 milliliters, the pH goes up from 0 a little bit, and then it goes up some more, up some more, up some more. And then we see that it kind of gradually starts to go faster and faster. And that's just because as you get closer to the equivalence point, you have less and less moles of excess acid around. So this thing starts to rise dramatically. Now, let's take a look at the equivalence point because it's kind of interesting what happens at the equivalence point. So when we get to the equivalence point, let's think about this in terms of excess and limiting reagent. So before the equivalence point, we have 50 mils of a 1 molar HCl solution, and we're starting to add in some base. So our excess reagent is HCl. So that's why the pH is still below 7, because before we get to the equivalence point, the HCl is in excess. We haven't added enough base to fully react with it yet. So it makes sense that we're down here in the pH is below 7. And then when we get past the equivalence point, we start to go into pHs that are above 7, because now the excess reagent switches from HCl to NaOH. As we continue to add in NaOH beyond the equivalence point, our pH is going to go past neutral and then up into the basic area. Now, what's interesting is at the equivalence point, we have just enough HCl to react with NaOH. So our products are going to be water and NaCl. And both water and NaCl are neutral compounds. So you'll notice that if you carry this over at the equivalence point, where we've reacted all of our HCl and all of our NaOH, because the number of moles are equivalent, we get a pH that's at exactly 7. And that's because all we have in that solution is water and NaCl. Now, on either side of that equivalence point, one of these two things is going to be in excess. So now let me just pop up what I was kind of trying to say and summarize it. So before the equivalence point, we have excess HCl. We haven't added in enough NaOH to react with all of our HCl yet. So the pH has to be less than 7 because we have acid around. Then, when we get to the equivalence point, our pH becomes 7 because we have exactly the same number of moles of HCl and NaOH. All that's in that solution is water and NaCl. Then when we start to add in more NaOH than we have HCl, we start to get an excess of NaOH, and our limiting reagent becomes HCl. So the pH now becomes greater than 7 because we have base around. So now we've kind of dissected this titration curve, and we understand why we have this shape. Now the rapid rise at close to the equivalence point is due to the fact that we're starting to get to very, very small concentration of whatever our excess reagent is. The excess reagent gets very, very close to being almost not even in excess at all. So the pH changes very rapidly here because adding a small amount of NaOH is going to start to overwhelm that little bit of excess HCl, and then the pH rises dramatically through the equivalence point. Now let's look at indicators and let's compare the equivalence point to what we call the endpoint. So an indicator provides a visual cue for approximately when the equivalence point is reached. So if we don't have a pH meter, we need something else to tell us when we reach the equivalence point. Now in the next lab, we're actually going to learn how to interpret this shape and determine the equivalence point by knowing the fact that this rapid rise happens through the equivalence point. However, in this experiment, we're not going to use a pH meter. We're going to use an indicator, which is going to tell us when we reach approximately the equivalence point. And the indicator that we're going to use is phenolphthalein. So phenolphthalein is a weak acid that is colorless in acidic media and turns bright pink in basic media. So from pH 0 to 8.2, this thing has no color. So here, this is pH 7. You can see the phenolphthalein is completely colorless. And then when you go through pH of 8.2, when you get above a pH of 8.2, the color turns this pinkish color. So this is the structure of phenolphthalein, and these are the protons that can come off and react with the base. So this is a diprotic weak acid. And when you start to take these protons off, that's when it becomes colored. So now let's compare the endpoint to the equivalence point. So let's just take a look at this graph. Now what I've done on this graph is I've put on the graph where we start to get a color change relative to the equivalence point. So the equivalence point is right here. So the equivalence point should by definition be at exactly a pH of 7. Now phenolphthalein, although it's pretty good, it doesn't change color until 8.2. So when we get to the equivalence point, we're still actually not going to be able to see or tell that anything has happened. It's not until we add a teeny bit more base to get us up to a pH of 8.2, which is right around here. So we have to add a tiny little bit of base beyond that before we start to get into this gradient area where the color changes, right? So you can see that the color change starts to begin at a pH of 8.2, which is kind of like right about here. We start to get into our pink gradient, and then it gets darker and darker and darker as you go into more and more base. So the problem with an indicator is that, generally speaking, they're very close, but oftentimes they only approximate the equivalence point. So meaning you have to tend to go a little bit past the equivalence point in order for you to get a color change. So we call this the endpoint. The endpoint is the point in volume in a titration when the indicator actually changes color. So it's an approximation of the equivalence point. This should say provides a very close approximation of the equivalence point, not the endpoint. But it's not exactly when the endpoint happens, and that's because of this slight delay due to the fact that the indicator doesn't change until a pH of 8.2. So now let's look at today's reaction. So today's reaction involves the reaction of potassium hydrogen phthalate, we know this as KHP, with a strong base NaOH. So potassium hydrogen phthalate is actually a weak acid. Unlike the strong acid, strong base that we did in the previous example, KHP is actually a weak acid. And the reason for that is because you know that hydrogen phthalate or potassium hydrogen phthalate is not in the table of strong bases in the textbook. So we're doing a weak acid strong base reaction, and we're using an indicator to determine the endpoint. So now how does this work? Well, when we react this potassium hydrogen phthalate, now you'll notice that the potassium hydrogen phthalate, this is actually a salt. So this entire structure here has a negative charge, and the potassium that's there is a counter ion to balance out the charge. And then the hydrogen, this H that's indicated over here to the left, is the acidic proton that's attached over here on this OH group. So this is the acidic proton that's going to come off. And the acidic proton is going to react with the OH minus from the strong base NaOH to give H2O, and a new compound, which is the potassium, the sodium potassium form of the phthalate. So this is sodium potassium phthalate, or what we call dibasic phthalate. And the sodium comes from the Na and is used to balance out the charge, the minus charge that comes from the fact that we've deprotonated this O. So now the counter ions are both sodium and potassium. And these will just hang out in solution because they're spectators. And then because we're doing a proton transfer to the OH minus, we make water as our other product. So that's what's going on with the reaction today. So now you kind of have an understanding of the chemistry in terms of weak acid reacting with a strong base. So the first part of this experiment is the standardization of a solution of NaOH. So we have to make our titrant, and we have to get the precise concentration of that titrant. So how do we go about making a solution of NaOH that we're going to use as our titrant? So in lab, what we would have is we would have a concentrated NaOH solution. This is approximately 19 molar. And the reason why it's approximate is because NaOH is a strong base, and it's known to pick up carbon. Carbon dioxide readily dissolves into NaOH and strong basic solutions in water, forming carbonates. So this 19 molar is approximate because there is some carbon dioxide that's been dissolved into that solution. So the whole purpose of all of this is to, knowing the fact that this is approximate and that we're going to dilute this to an approximate volume, we're going to have to standardize that so that we can actually figure out what the precise concentration of that NaOH solution is. So we're going to use a graduated cylinder to add about 4 mils of concentrated NaOH to a plastic bottle. The plastic bottle looks just like this. And then we're going to wash that graduated cylinder a few times with deionized water just to get all the NaOH in. And then finally, we're going to fill the bottle to the neck with deionized water. So again, this is not graduated, or we have no accurate measurement of the volume. So again, this is going to be very approximately 1.1. So we got to figure out exactly what that number is. Then we're going to shake this all up just to gently mix it together. Now, the second step is to get that exact concentration. So when we're doing this, what we're going to do in this part of the experiment, and this is a bit backwards, but so let me explain what we're going to do. So now we have our approximately 0.1 molar NaOH in our burette. Oops. And then we have down here where we're going to have a KHP standard, and we're going to use the KHP standard to work back and figure out, hey, what was my concentration of NaOH? So our unknown in this case is the concentration of the NaOH, and in a flipping of the experiment, that unknown is in the burette. But that's okay, because it doesn't really make a difference where the unknown is, as long as we know where the known is and where the unknown is. So the unknown is the concentration of NaOH, and that NaOH is in the burette. And then the known is the mass of the KHP. So in this part of the experiment, we're going to use a KHP standard. It's a 100% KHP standard powder. It's a very, very, very pure KHP standard that we're going to use. And that's how we're going to figure out the concentration of what the NaOH is. So we're going to weigh out 0.4 to 0.6 grams of pure 100% KHP, and we're going to note the mass very accurately in our data sheet. And we're going to do this 3 times. So we're going to get 3 Erlenmeyer flasks. We're going to weigh out about 0.4 to 0.6 grams into those 3 flasks. And we're going to note those weights to 4 significant figures for each of the flasks. So we're going to have a very accurate measure of how much of the KHP standard we have. Then in each of those, we're going to dissolve the KHP in about 100 mils of water. And we're going to add we're going to add 2 drops of our phenolphthalein indicator. So that is what's going to make us have the color change. And then we're going to perform our titration as we did in the video. So now we have our KHP standard, we have our sodium hydroxide. We're going to rinse the burette a few times with the sodium hydroxide solution. And then we're going to fill the burette with the 0.1 molar NaOH and perform the titration. Okay, so let's look at an example of how we do the calculation for the standardization and what the experimental data will look like. So in this example data, this is actually not from an experiment, but this is something that I created from my own data, meaning this is not one of the 3 replicates that you're going to be calculating. But this is just sample data in order for us to look at how we do the calculation. So in order to determine the concentration of NaOH, which is what we're doing, so the unknown in the standardization is this concentration of NaOH, we need to have 2 things. We need to have the number of moles of the NaOH, and we need to have the volume in liters that the number of moles were contained in. So we're going to look at how we can measure how we can calculate these 2 variables in order to get the concentration. So here's what we basically have. We have an initial burette reading. This is where we started. And then we have the final burette reading. This is where we ended, and this is when we reached the endpoint where the thing turned pink. And so from that, we can get a volume of the NaOH. And that volume of the NaOH is what's going to go down here, right? That's the volume that we added in to get to the equivalence point. Now, the other thing we need is the number of moles. So the number of moles is going to come from the fact that we know how much KHP we put in. We have a massive KHP, we can convert this to a number of moles of KHP, and then at the equivalence point, we know that the moles of KHP is equal to the moles of NaOH. So let's start to execute on some of these calculations. So the first part is to get the moles of the NaOH, and to do that, we take our 0.5128 grams of KHP, and we have to convert that to moles doing stoichiometry. So we're going to divide this by the molecular weight of KHP, which is 204.23 grams. That's going to get us to moles. And then the most important thing is at the equivalence point, we know that for every 1 mole of KHP, there's 1 mole of NaOH. So we get 2.5109 times 10 to the minus 3 moles of NaOH. Now, this is the only time I'm going to do this, but I just want to remind you that whenever you're doing these calculations, because we're carrying a lot of significant figures, you should always carry 1 or 2 extra significant figures in all of your calculations. And the reason for that is because we want to make sure we get very accurate results. So don't round any number until the very end of the calculation for this, or else you may run into a problem. So now we have the top part. We have the moles of NaOH by doing stoichiometry. And the bottom part comes from the volume of NaOH that we added. So we take our final volume, 24.61. We subtract away the initial volume that we read. And that gives us a total of 20.35 mLs that was added. So I'm going to write that down here. And then because we need the volume in liters, I'm going to also convert this to liters by dividing by 1,000. So 20.35 is equivalent to 0.02035 liters. And then at this point, we can calculate the concentration by taking our number of moles, dividing it by our liters, and we can get our concentration. So our concentration in this case was 0.1234. So you could tell that it was made up. If any of you guys know Spaceballs, this was the combination on his luggage. So now in real life, that was sample data that gave the 0.1234. In real life, this is the data that you would have gotten if you were to run this experiment. So when you went into the lab, you would have measured 0.6059, 0.6064, 0.6039. Now notice that these are all to four decimal places, and that's because that's the maximum number of decimal places that the balance can give you. And then we have our initial and final burette readings. So when you went into the lab, you kept your initial burette readings at around 1.5. That's what you filled it up to. And then you got final volume readings at around 30.58, 30.62, and 30.86. So now your job is to calculate the milliliters of NaOH that's used and the molarity of NaOH. And you're going to get 3 different molarities from these 3 different trials. And then you can calculate the average and the standard deviation. So you'll show your calculations for the molarity and the standard deviation below. So the important thing is the reason why we run 3 replicates is we want to make sure that we get a very reproducible result, that our precision and our accuracy is correct, meaning that when we run this multiple times, we get numbers that are very close to each other. And that will be evident in the standard deviation. Generally speaking, we want our standard deviation to be at or less than 1% of the average. Okay, so now let's look at the second part. So in the first part, we spent a lot of time figuring out what our exact concentration of NaOH was. So in the sample data, we now know to 4 significant figures that the concentration of this NaOH was 0.1234. Now in your data, it's going to be some other average, but in mine, I got 0.1234. So that's why we did the standardizing. So now we're going to use that standardized NaOH to work on figuring out KHP in an unknown sample. So now we're going to use a different sample of KHP that's going to be a mixture of KHP and something else that we don't really care about, but we want to know what is the percent of KHP by mass in that unknown. So we want to figure out the percent mass of KHP. So the unknown in this case is going to be the KHP sample containing an unknown percent of KHP, which is our analyte, and that's going to be in our flask. So there's our KHP unknown. And then our known is the standardized NaOH solution, which is our titrant, and that's in the burette. So assuming that the unknown contains, so the way that we're going to do this, the way that we're going to prepare our solution, is we're going to do a calculation where we assume that the unknown contains about 75% of KHP. And then what you guys have to do is calculate the mass that would be required to use 20 mils of titrant. So in essence, we're doing this calculation here, right? We're calculating the mass, but we're going to assume that it's about 0.75, that is about 0.75 or 75% of the KHP. So I want you guys to work on this calculation on your own. Make sure that you know how to do it. I'm not actually going to do it because it's not 100% relevant to the lab. But if for some reason you don't understand how to do this calculation or you have a question, you can contact your section instructor and they can help you walk you through this calculation. And the reason why we're doing this is because we just don't know what percent of KHP it's going to be. So, we can't tell you a hard and fast number for how much to weigh out. You kind of have to think about it. So this case is saying, well, let's take 75% as a representative percentage. And we'll kind of work back from 75% to figure out, hey, how much would I have to weigh out in order to get a reasonable amount of titrant? And that reasonable amount of titrant would be about 20 mils. So we're kind of using some approximate values to figure out how much I have to weigh out. So once you do that calculation, you're going to weigh out the unknown based on the calculation above and dissolve it in 100 mils of deionized water. So you have to do this calculation in order to figure out how much you would weigh out. And then you're going to add 2 drops of phenolphthalein. Again, you're preparing 3 trials, so you're going to weigh out whatever you calculated into 3 different Erlenmeyer flasks. And then you add 2 drops of phenolphthalein, which is our indicator, and then you're going to perform the titration. So now let's look at some example data. So for this one, I'm just, again, this is going to be some data that I did in the lab that I kind of made up. And we're going to use this as an example to show you how to do some calculations. So now the question is how can we figure out the unknown KHP percent? How can we figure out the percent composition in the unknown? So now what do we have to start with? Well, we have the mass of the unknown, 0.5278 grams. That's how much I weighed out. We have the final burette reading. I'm sorry, this is flipped. This is flipped here. So this should be, the final burette should be 15.25 mils, and the initial should have been 3.47. So I started at 3.47 and went to 15.25. So now, what do we need to do in order to get the percent composition? Well, in this case, what we're going to do is, the first thing we have to do is figure out, well, how much NaOH did I add? So I added 11.78 mils, or 0.01178 liters of NaOH. And I do that by subtracting the 3.47 from the 15.25. Now, the reason why we need the volume of NaOH that's used is because if I know the volume of NaOH, I can use the exact concentration that I measured from my previous sample data to come up with the number of moles of NaOH. So we have 0.01178 liters of NaOH, and from my sample data, I had 0.1234 moles of NaOH per liter. This is my molar concentration. Now, you're going to use your calculated value from the previous example, right? So you're not going to use 0.1234. You're going to use whatever you determined as the experimental average in the previous in your previous calculations. But this is just a sample to show you what the calculations look like. So now we know that when we reach the equivalence point, which is this was the volume that was required to turn the solution pink, for every 1 mole of NaOH, I have 1 mole of KHP. And then from every 1 mole of KHP, I have 204.23 grams, which is the molecular weight. So now I know, because this is the amount of NaOH I added, and this is my standardized concentration, I can now work back to figure out how many grams of KHP were in that solution based on the equivalence point. And then if we want to figure out a percent composition by mass, we have to know what is the mass of KHP divided by the total mass of the unknown times 100. So the mass of KHP was 0.2969 grams, divided by the total mass, which was 0.5278 grams times 100. And in this particular instance, I got 56.25% for my percent KHP. So again, your numbers are going to be different, especially this number, which is going to be your average concentration from your calculations. But this setup will be the same, and that's how you're going to get the percent KHP. So now here is the experimental data that you would get. So again, these students, the digital students, the virtual students, measured out a mass of around 0.6033 grams. So they went for around 0.6 grams. And then for their final and initial burette readings, those are here. So you guys now have the ability to do the calculations. You can get the mils of the NaOH that was used, the mass of the KHP that was in the unknown, and then the percent. And again, we're going to calculate the average percent of the KHP and the standard deviation. You're going to do that here. And then down below, you can show your calculations on the data sheet. So just to kind of recap a few important things, in this experiment, we take you through both the standardization step and through the titration of an unknown analyte step part of it. And what you'll notice is that you're going to see two or three different approaches to doing the calculations. But in general, the starting point of those calculations has to start with, what do I know and what do I not know? And where is the known? Is it in the flask or in the burette? And where is the unknown? Is it in the flask or in the burette? Once you know what the known and unknown are, and you have that kind of written down on your paper, then you know where you're going to get your number of moles from. The number of moles are always going to come from the known, right? So let's just kind of recap that a little bit. In part 2, our known was the standard NaOH solution, and you see that I used that to get the number of moles and the number of grams of the KHP. In the previous case, my known, let's get to it. My known was the mass of KHP dissolved in the water. This was in the standardization of NaOH. So when I do my calculations, the number of moles comes from the known. So the known always gives you the number of moles. And then the unknown, we're using that number of moles to figure out whatever information we want to know about the unknown, whether it's a concentration or a percentage. So that should help you sort of set up these calculations as you go along. The other thing that I kind of want to mention at this point is whenever you're doing a titration, you have to keep in mind the difference between the equivalence point and the endpoint. So in doing all of these titrations and using a indicator, there is going to be a systematic inaccuracy. It'll be very, very small, but there will be a small systematic inaccuracy in all of those measurements. And that's due to the fact that the endpoint is slightly past the true equivalence point because it takes a couple of extra micromoles or millimoles of NaOH to get that indicator to turn, meaning we have to go up to a pH of 8.2, which is slightly past the equivalence point of a pH of 7. So that's something to think about in terms of the accuracy of what you can achieve with a titration done with an indicator. Now in the next titration, we're going to use a pH probe, and that's going to allow for a much more direct measurement of the equivalence point. So keep in mind, guys, that this will be due on the day that the syllabus says that it's due, so make sure you're staying on top of the syllabus. If you have any questions, you can ask your section instructors. Otherwise, the calculations in this one are relatively straightforward and are very similar to what we did in class.